Okay, so now we'll get back to one sample means. Yay, exciting! So this is chapter 7 in your book. Chapter 7 goes into so much more detail than I expect you to absorb from this class. So refer to it. Don't try and memorize every single page of that textbook chapter. Same goes for pretty much the rest of the class. Skim through it, use it as a reference, use the lectures and other things I put on D2L as your main source of how to do what you're doing in the homeworks. Okay. So a brief review, descriptive statistics, what you did in homework 3 and homework 4 were descriptive statistics. So finding frequencies and percents or finding the mean and standard deviation. Inferential statistics are what we're going to start doing next week. So this allows us to see if there really is a difference between two groups. Whereas before we were just describing them, this inferential stuff lets us see if there's a difference between those two groups. That gets really fun and exciting. Okay, maybe not, but I think it is, so it's fine. So some characteristics of sampling a distribution of the mean. So the mean of a distribution is the funky looking U symbol. So this middle point. Symmetry is approximately normal, which means that both sides look pretty much the same. If you cut the middle here and flip them on top of each other like a hot dog roll, I don't know why I thought of that, but that's what came to mind, they would match up. Then the variability is the standard error of the mean. So the average standard deviation of the sample mean from the population mean. So if we have the population mean and we have the population standard deviation, and then we take one sample from that population, we will have a sample mean and a sample standard deviation, which may be similar but not exactly the same as the whole population. So that's error of standard error of the mean is the difference between those. And it's measured by this fun formula here, which you don't need to memorize. You don't have to memorize anything because you have access to everything when you're doing your homework. Okay. A little bit about the central limit theorem is that sample means are approximately normally distributed. We're making this assumption, again, for the rest of the class. So the mean is this U symbol and the standard deviation is equal to the standard error of the mean. If the sample is greater than or equal to 30, if the sample is less than 30, this is not true, and we'll talk about that a little bit later in this lecture, but if it's greater than or equal to 30, then this mean and the standard deviation are equal to the standard error of the mean. Okay. So here's an example. So we're going to teach some students reading skills in this program we're running, and we're going to see if they can, how many words per minute they can read correctly. So somehow we found out that in the normal population, children can read 124.81 words correctly per minute with a standard deviation of 43.26. How did we find this out? I have no clue, but we know it, so that's all that matters. I'm not going to ask you to magically look up numbers to try and find things like this. That's just crazy. Okay, so a sample of the population of 4th graders. So at this school we're looking at, we have 4th grade children in some program that they can read, correctly read 150.35 words per minute. So we want to know, does this reading program change reading ability? So did our program work is basically what we're looking at. So first we state our null hypothesis and alternative hypothesis. So the null hypothesis is this first one, that the mean is equal to 124.81. That's the population mean. Our second alternative hypothesis is that the mean of the population is not truly 124.81. So this means that if we accept this alternative hypothesis, that our mean is a more accurate representation of the population than this population mean, or there's some difference between our population and our sample. Okay. So we make a decision about the null hypothesis. So we set an alpha level. We're always going to use the alpha level of 0.05. So you don't really have to think about this, you just have to put 0.05. Because there's not a direction associated with this, we're not saying that we think that our mean is going to be higher than the population mean or our mean's lower than the population mean. We split that 5% region, 5% of this normal curve into two regions, which is one in each side here. That's just how it works. I don't know why, that's just how it works. So this section here and this section here fall in the standard normal curve, so that curve that has a mean of 0 and a standard deviation of 1 at the standard deviation of 1.96 and negative 1.96. So in order to make a decision if we're going to accept or reject the null hypothesis, we have to see if the z of our sample mean is less than negative 1.96 or if it's greater than 1.96. If it does fall into those regions, those tail regions, then we'll reject the null hypothesis. If it falls in between negative 1.96 and positive 1.96, then we do not reject the null hypothesis. Okay, so first we're going to calculate the statistics. So we're going to use this z formula again. And because we're using means, it kind of gets a little different. It just has this sub x mean in this bottom part. So to make a decision, first we have to find this standard deviation of the mean of your sample. So in order to do that, you use the population standard deviation divided by the square root of the n, or the number in your sample. So if we go back to the example, there's 20 people in this sample. So the sample mean, the population mean is 43.26 divided by the square root of 20. So when we do that math, you get the standard deviation of the sample that we took of those 20 people is 9.68. Now we plug that back into that z formula. So our mean of our sample, 150.35, minus the mean of the population, 124.81. Then we divide that number by the standard deviation of the mean that we just found on the previous slide. And then you get your z-score of 2.64. What do we do next? Okay, so we make a decision. So in order to make a decision, we have to see, okay, is 2.64 greater than 1.96 or less than negative 1.96? So does it fall into one of those categories? Yes. So therefore, we reject the null hypothesis. So basically what this is saying is, because our mean is different in our sample than the population, there is actually a difference. That's all it's saying. Which I know, it's a lot of work just to say that, but that's how it is. So here it is written out nicely. So the number of words correct per minute, the mean of 150.34, in our sample of 20 fourth graders was significantly greater than the national sample, the mean of 124.81. This is how you would write up a summary of this finding. So you would want to include the mean of your sample, the mean of your population, and then at the very end of the sentence, you include a comma, then the z-score you found, and then the p-value. So, because we saw that there was a difference, this last one we decided that 2.64 really is greater than 1.96. The p-value is less than 0.05. If we had found that the z-score was 1.21, then we would have accepted the null hypothesis, and then p would have been greater than or equal to 0.05, meaning that there was no difference between the population and the sample. So this was actually a study that was done. So what they wrote in their paper was, this study revealed that teaching an explicit systematic reading comprehension strategies to fourth graders is likely to increase reading comprehension skills. If you want to read more about it, your book has this source. Cool. Questions about this part? No? Okay. So, the things that we're going to assume for one mean. I know that this example had 20 and that doesn't make sense, but just pretend it didn't. For a z-test, your sample, you want to have 30 or more. You're going to assume that there was a random sample taken. It has to be continuous data. So that means not measured nominally, like gender, or ordinally, like the satisfaction rating of poor to excellent. And it has to be assumed, the curve has to be assumed to be normal. In your homework, these last three things, the random sample, continuous data, and assumption of normality, are all true. The thing you really have to look for to determine if you're going to use a z-test or a t-test is the sample size. So if it's 30 or more, you use a z-test. If it's less than 30, you use a t-test, which we're going to do soon. Now, actually. So here's another example. So a sample of 15 students scored an average of 23 points on some quiz. Based on other scores from previous semesters, the professor knew the scores were normally distributed with a mean of the population of previous quizzes of 20 and a standard deviation from previous quizzes of 5. So is this new sample, the current semester students, scoring significantly better than the population? So this is a directional hypothesis because we want to see if they're actually scoring better. The previous one, we just wanted to see if it was different. So that's why we used the two tails. This one we're going to use one tail, I think, because we just want to know if they're scoring better or not. So a student t-distribution means that there are less than 30 people in our sample. So the distribution of the values are the same as a normal distribution. And this is used to estimate the population when you don't know the standard deviation. Okay, so there's the formula for a t-score finding. So it's the population mean lies the sample mean minus the population mean divided by the standard deviation of the sample divided by the total number in your sample. So here's an example. I don't know why I didn't have the answer to the other example. I don't know about that. I'll have to look into that. When I figure it out, I'll post it for you guys. Sorry. So here's a different example. Do students perceive themselves to be invulnerable? So it's known in the US that people typically die at age 75. So a sample of 17 students was asked to predict when they think they're going to die. That's really morbid. This is a terrible example. This is what your book told me to talk to you about, so whatever. So their scores had the scores of those 17 students had an average of 84, with a sample standard deviation of 8.01. So does this sample show that these students think they'll live longer than the national average of 75? Super morbid, sorry. Should have read that a little more carefully. Would have changed it to something more exciting. Anyway, the null hypothesis is that the population mean is equal to 75, and the alternative hypothesis is that the population mean is not equal to 75. So then we make a decision about the null hypothesis. Since we have a group less than 30, we have to calculate the degrees of freedom. So what the degrees of freedom means is that there is one less possibility than the total number of in the sample, which totally doesn't make any sense. But all you have to remember is that degrees of freedom, or DF, is equal to the number in your sample minus 1. That's what you need to know. So we're just going to leave it at that. That's what you need to know. DF equals n minus 1. Cool. So our sample size is 17, so 17 minus 1 is 16. So we'll need to know that in a minute. But then we set our A, our alpha level, which again will always be 0.05. And this is two-tailed because we are not looking at a specific direction. We just want to see if there's a difference. Cool. So to find this 2.12 value, I don't have it on here, but I will open up D2L and show you where you can find it. So what we want to see is if our t value that we're going to calculate is above 2.120 or below negative 2.120. If it is, we will reject the null hypothesis because that means our sample is truly different than the population. If it falls somewhere between negative 2.120 and positive 2.120, then we do not reject the null hypothesis, meaning that our sample and our population have similar means. So we calculate it using this fun formula. Yay! So we use first we have to find this, the standard deviation of our sample. So to do that, we use the standard deviation of the population divided by the sample, the number in the sample. So 8.01 divided by the square root of 17 equals 1.94. Then we put that into the t formula here, and you get the mean of 84 minus the mean of the sample of 84 minus the mean of the population, 75, divided by that value we just found, 1.94. And that gives us a t value of 4.63. So now, are we going to accept or reject the null hypothesis? Who thinks we're going to accept it? Don't look. Who thinks we're going to reject it? Yay! We're going to reject it because 4.63, the t value we found, is higher than 2.12, which is that cutoff value. If it was less than that, then we would accept the null hypothesis. But because it's greater, we reject the null hypothesis. So to write that up, you would say that the average estimated age of death, the sample mean of 84 for the 17 class members in this sample was significantly greater than the population average of 75 years. Then at the end of that sentence, you write T, in parentheses, is your degrees of freedom value. So that 16 we calculated, n minus 1, 17 minus 1 equals 16. That's where you'll put that, equals the t value we found, 4.63. And then because we rejected the null hypothesis, the p is less than 0.05. Okay. Another way to write that would be that the results support the research hypothesis that people provide estimates that are greater than the actual life expectancy of the population. So some assumptions of this t-test we just talked about. The sample size is less than 30. There's random sampling, which there always will be in your homework. There's continuous data, there will be in your homework. And there's an assumption of normality, which will also happen in your homework. Because otherwise it goes even crazier. We're not going to go there. Because this is crazy enough, I know. Questions to hear? Okay. Okay, we have 3 more slides, then we're going to take a little break so that you all can breathe for a minute. So, factors influencing the decision about the null hypothesis. The sample size. So the larger your sample size, the greater the probability that you will reject the null hypothesis. So the larger the sample size, the greater the chance that your sample will be the same as the population. Which makes sense, right? If you have a sample size that's closer to the total population, there's a greater chance that you're going to get the same results. If your sample size is way smaller than the total population, there's less of a chance that you're going to get the same results that you got in the whole population. Think of it this way. If I took a sample of everyone's grade in the whole class, there's one average. Let's say it's 89, because I'm going to make it hard. So it's an 89 for the whole class. And then I take a sample of one person, and their score is a 97. Well, does that represent the population? Not really, because the total sample has a mean of 89. But if I were to take a sample of everyone except the people that aren't here today, maybe my average would be a 92, which is closer to that mean of the whole class. Does that make sense? Because there's more of you than just one person. But it's not everyone. Okay. And then there's some examples here that's calculated out for you so you can see the differences. That's also in your book. Some other factors, the alpha level. So the larger the value of alpha, that 0.05, so that can be changed. We won't change it in this class because that gets confusing with that degrees of freedom table. But if you were to change that out in the real world, the larger the value, the greater the chance that you'll reject the null hypothesis. Which means the larger that A is. So if we put an A of 0.1 instead of 0.05, that means we're less sure of what our answer is. We're not as confident in what our answer is, the higher this A value is. So if we had an A of 0.01, that means we're even more confident in our answer than if we had an A of 0.05. So if your homework asks about the change in the alpha value and rejecting the null hypothesis, the larger the A, the more chance that you will reject the null hypothesis. The smaller the A, the less likely that you'll reject the null hypothesis. Okay. Also the direction. So there's a greater chance of rejecting the null hypothesis if you use one tail. So if we say that we expect the answer to be greater than the population versus saying that we just expect it to be different. Okay. Take 5-ish minutes. We'll start at 35. How's that sound? 5:35. So get up, walk around, take a breath. Don't think about this for 10 minutes so that you can reset for the last part.
Yeah. 20.